Welcome to the 29th lecture for Physics 4B. In this lecture, we complete our coverage of the complete unified theory of electromagnetism. We use the Maxwell's equations we discussed in the last lecture to derive a wave equation for electric fields. And nearly identical derivation can be done for magnetic fields too. This derivation amounts to a prediction for an electromagnetic wave that travels at the speed of light, a prediction that was confirmed by Hertz experimentally. In the second half of the lecture, we look at some properties of electromagnetic waves. We first look at the relative orientations of the electric field, the magnetic field, and the propagation direction. The propagation direction, in particular, is parallel to what we call Poynting vector with y, which has some physical significance discussed in the last lecture segment, alongside some mentions of the applications of electromagnetic waves. This is the penultimate lecture video in this video set for Physics 4B. In the next, that is, ultimate, lecture video, we will do a review of topics since the last review, work through some exam type problems, and demonstrate some useful problem-solving tools. So this is what we have covered so far. Maxwell's equations, the set of 4 equations, which I keep telling you describes everything we need to know about electricity and magnetism. I guess to tell you the truth, it's everything about electricity and magnetism as long as you are in vacuum. Because we keep using this permittivity of free space and permeability of free space. So once you start talking about something in a linear medium, then that's where you have to do a bunch more stuff. That's upper division material. I'm not going to do that. But this equation describes everything we know about electricity and magnetism in vacuum. And so in the afternoon session, we just I introduced these as the differential form, and I wrote down some stuff for those of you who have not taken Math 3C, so that these new symbols you are seeing makes some sense. This is a vector operator that takes this form. And when you are using it, you use it more or less like a vector. So when you take a dot product, it looks like a dot product. And when you take a cross product, it looks like a cross product with some care in the ordering of the terms. So there was some, and I guess this is really for people who have taken Math 3C or are currently taking it. You can actually see easily, or without too much difficulty, you can go from here to here. It's actually more difficult to go the other way. That's why I don't bother trying to derive these expressions from this, because it's a little bit too hard. But once you have this as a given, then to go from here to here, all you really need is application of, I always forget these terms. To tell you the truth, I never actually took multivariable calculus properly. I just took upper division electrodynamics, and they counted it as a multivariable calculus in my school. But to go from here to here, it's an application of, I think, a Gauss's theorem. Is Gauss's theorem something you learn in Math 3C? Yes? Yeah, so this is an application of Gauss's theorem. You do a volume integral on both sides. Right-hand side becomes this. And left-hand side simplifies to an area integral by using Gauss's theorem. Right? Same thing with this. And these, you use a Stokes theorem. You do an area integral on both sides. And right-hand side becomes current enclosed and flux, all that stuff. And the left-hand side becomes this a line integral by application of Stokes theorem. So that's why this form is preferred. It's the simpler form. If you want to prove anything, it's a lot easier to start out with the differential form and then branch out from there. We use the whole semester the integral form because the assumption is that you haven't taken Math 3C. If you are going through the sequence that's recommended for engineering majors, then you should be taking 3C right now as a core requisite. So that's why I feel now a little bit more comfortable to talk about this form, because I think, well, more than half of you have seen notations here. So it's a couple of you who haven't, this is not going to be on the exam anyway. So the reason I'm introducing this form is I want to use this to talk about the electromagnetic wave. So do you guys remember from end of last semester when we were doing physics 4A, what we called the wave equation, like rough form of that? Yes, you remember the phrase, the wave equation. What was the wave equation, just as a qualitative description? Chris?
I want to say that it had like sine and cosine and it had the phase thing.
You are thinking of the solution to the wave equation, right? So if you have a periodic traveling solution, you could write it that way. But wave equation, it's a form of, I don't know if you guys remember this phrase, equation of motion. So it's a particular type of equation. Anybody here remember what type of equation it looked like? No one here? Yeah, I guess many of you probably haven't taken the class where you might have seen it. You would have seen it in Math 3F, the differential equations class. It's a differential equation. So let me write it down here as a reminder. So the wave equation, so we introduced it early, starting with physics 4A, because you are going to see this equation in every physics class. And it's important in some of the applications. So anyway, so let me write it down. So it describes a wave, which can be a wave, which is going to be a function of position and time. And this position is potentially it's three-dimensionally specified. And this function itself, it can be a vector, and it also can be a scalar. So a scalar wave would be like a sound wave is a scalar, because it's a wave of pressure, and pressure is actually a scalar quantity. It's not it's like temperature and pressure. It's a scalar quantity. Or this can be vector also. In the case of the electromagnetic wave that we are going to talk about, this will be vector. So if it's a vector, what you have to imagine is we are dealing with the x, y, and z component of wave. So I can just talk about a single component, and if you're dealing with a vector quantity, you can extend it to other components that may be there. So you're dealing with an equation that describes a function which is a representation of wave, and this is the form of the equation. It says let me write it down in 1D, and I will write down the version for 3 dimensions, but we're not going to deal with it. The version for 1D is that double spatial derivative with respect to one direction, let's say x, that's the direction of propagation. That's the direction the wave is moving. Double spatial derivative of the function is equal to 1 over v squared times double time derivative of the same function. This is the wave equation. And this v, the constant for this is written as 1 over v squared for a good reason. The constant that appears here does happen to be actual wave speed. Did all of this begin to look familiar? I know we covered it. Actually, one of the reasons I actually made the physics 4A exam cumulative, the final exam cumulative. One of the reasons was I was finding some people were getting through the physics 4A class without bothering to learn a lot about waves. I wanted to make sure that those people didn't get an A. So, but this is something that you are going to see again. It's not something obscure I'm bringing out of nowhere. It's
If you take physics 4C, you are not going to see this specific wave equation, but you do deal with the wave equation, the quantum mechanical wave equation. So the concepts we are discussing now is something that will come up again and again. So I guess while I'm writing that down, since I went through all this trouble to introduce these notations, let me write down the three-dimensional version. The three-dimensional version of wave equation looks like this. You have, so this double spatial derivative, it becomes the gradient dotted to itself. So let me write that as, I'll write it down properly. Gradient dotted to itself. So that gives you the double spatial derivative. Or acting on f is equal to 1 over v squared. And time is just time. It's not, I don't have to do anything special with it. So if we are dealing in the 3 dimensions, the only thing that really changes is the this portion of the equation changes to reflect that the wave can be moving in any 3-dimensional direction. You do have to still pick one direction to go, but it's 3-dimensional. So that's the wave equation. And the reason I'm introducing this is because we are going to get an equation that kind of looks like this, starting out from these laws of electricity and magnetism. And I think I did the derivation for you guys last semester. So I did the derivation for wave on a string. As in, we looked at the equation of motion for an outstretched string, and we looked at what the equation of motion for this would look like if I imagine that there's some bend in the thing and see what that would look like. And we got some equation that looks like this. And one of the payoff from that was when you are deriving that, when you are going through that equation of motion, and when you derive an expression, I got out of that equation of motion, I got the coefficient that would fit into this portion. And in case of wave on a string, this coefficient ended up being, I guess, mu over t, where mu is the linear mass density, t is tension, and this meant that the wave speed on string was square root of t over mu. I don't know. I'm pretty sure I derived it. Or, you can look at it in the textbook. But, so this would be actually one of the goals of going through this derivation. So, you are analyzing a medium that a wave can be in, and by going through the equation of motion that describes how the motion happens once, some part moves and there's a force on it, that one of the expected result from that is not the equation itself. You kind of have an idea that you are going to get to this. What you really are hoping to get that you didn't know before is what is the velocity? What is the expression for the velocity? So we are going to go through something similar here. We are going to start out with the Maxwell's equation, and we will go through some manipulation of these formulas. We'll plug something into the other with the goal in mind that in the end, we want to get an equation that looks kind of like this. And we'll see what coefficient ends up in this spot, and that'll tell us what the speed of this electromagnetic wave is. I guess for a lot of people, this is like watching a detective story where you already know the ending. So you know what the speed will turn out to be, but this will be the derivation for that speed. So let me introduce a couple simplifications, because the whole 3-dimensional derivation, it's too complicated. I don't want to do it. So I'm going to simplify some things to make sure I can actually go through the derivation without getting stuck. I guess let me write down the very first simplifying step that I'm going to do. So the very first simplifying step I'm going to make is, this is what I'm going to say. So to generate this wave, we do have to have a charge somewhere. So there's a charge somewhere in space. And this charge, from what you know, it actually has to be moving up and down. It has to be accelerating up and down in a sort of oscillatory way. And this is the simplifying step I'm going to make. I'm not going to say that I'm anywhere near the charge. So I'm not going to have to deal with a time-varying charge distribution. In fact, I'm going to be very, very far away from charge, way over here, where there's no charge, there's no current. Now there is this charge here, and it's moving up and down, can be looked at as current. But this is one of the benefits of dealing with this differential form of Maxwell's equation. These are all locally specified quantities. This is a quantity that I calculate at a particular point in space locally. If I can say that at this point in space, there's no charge, then I can make charge density go to 0. If I can say that at this point in space, there's no current, I can say that I can make current to go to 0. So this is not a step that I would have done before, because before that would have resulted in something boring. So let me write it down. So I'm looking at in a region of space with density equal to 0 and current density equal to 0. If I do that, then these equations become the divergence of electric field is 0, because in that particular location I'm looking, there's no charge. The divergence of magnetic field was always 0. And the curl of magnetic field now is a little bit simpler. The first term is 0, but well, I have to have electric field. If I say electric field is also 0, then that means I'm very, very far away from any charge. Nothing's actually happening. So I'm just going to have the electric field term. So mu naught, epsilon naught, and the time derivative of the electric field. Oh, I think I've been a little bit sloppy. Let me correct my sloppiness from earlier. I should have said that this is a partial derivative with respect to time. And what it really means is that, so for this variation, I'm only concerned with how electric field is changing as a function of time. Now, if there's something else that's changing, like a position of charge, then I'm going to ignore that kind of time dependence. All I'm looking for is the explicit time dependence. So with the correction, this should actually be the time derivative, partial derivative in time. It's a fine correction. It's not something that we would have paid all that much attention to in the first place. All right, so the curl of electric field looks like the time derivative minus time derivative of the magnetic field. So this is the simplified Maxwell's equation in, I guess, actual vacuum, where there's no charge, there's no nothing. And before I wouldn't have done this, because before even the third term would have been 0, and it would have been just so much easier to say, well, everything is 0. This is also, B is 0, so this is 0. But once we have these two terms, they can play off of each other and give us something that's non-trivial and meaningful. So this is the very first simplification I'm doing. That just to say that whatever oscillating charge that I have, whatever oscillating charge is relatively far away, so that at this point in space where I'm analyzing Maxwell's equations, I can say my charge density is 0 at this point in space. Let me make a couple more simplifications. So it comes down to, I don't really want to deal with the whole three-dimensional thing, because that requires me to have remembered the triple product and bunch of stuff that I frankly forget. Unless I review it, I'm not going to remember it. So I just want to deal with as few dimensions as possible. So let's see, what can I say? I think, let me set up my coordinate system first. So I guess I'll keep it to that system here. Let's say my x direction goes this way, and my y direction goes this way, and my z direction goes this way. X, Y, Z, yeah. All right, so I do want to look at a charge that's potentially moving up and down. Or I do want to consider something that's physically real, that's producing wave. But let me say I'm going to only deal with what's called a plane wave. It's a wave where the wave front looks like a plane. So not airplane, but geometric plane. So what would be meant by wave front is, so you know what a wave looks like, right? I don't have a good thing to illustrate wave with. So let me do it with this one. So you know what, roughly speaking, wave looks like. I'm talking to people who have an idea of shape of wave. So if you have something that's periodic, then you can look at something like this, right? And wave plane would be a plane of points over a particular point on the wave. So like that peak here, that would be a point that you can use to define wave front. And so, so this is a one-dimensional wave. So it really has only one point. But imagine this oscillating, sort of extended. So you'll have to imagine this oscillating is extended all along the horizontal plane. So imagine a series of these slinkers here, 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 and at each of the points in space, you can identify a slinky that has some displacement. And imagine this extended in layers along the vertical direction also. So in that case, I can take a point that looks like this bump and have a plane that connects all the points that have the same displacement. That would be the plane that's defining the wave front. And in general, it's not actually a plane. So if you have a source of wave that's maybe moving in circle like this, then this would generate waves that are kind of going out in spheres. But here I'm saying I'm so far away from this source that when I look at those wave fronts, I can approximate them as a plane. Mathematically, this is what it means. So if I'm dealing with a plane wave, then let's say I'm going to deal with electric fields. So I will eventually write down something that describes electric field. If I say I'm going to be dealing with the plane waves, so this is what it means. I pick a direction of wave propagation. So here, let's say wave is going in the x direction. Then by saying plane wave, I'm saying my electric field is only a function of x. It's not a function of y or z. Because as you move along y, your electric field shouldn't change if your wave front is going to represent a plane. So what this also means is, the x component is a function of x alone, y component is function of x alone, plus the z component is function of x alone. Good? All right, so this will help me simplify some of these equations. You will see how it simplifies once I actually write them down. Write it out in the component form with the help of these expressions for divergence and curl. So let me do that. I think that's the simplest way to show why I'm making this assumption and why that helps me. So take this electric field, for the Gauss's law, for example. So writing out the divergence like this, or it looks like a dot product. It says the x component of this plus y plus z is equal to 0. Right? But when you look at it carefully and keep this in mind, you should realize that the second and the third term immediately go to 0. Yes? Right? Oh, G is, well, it doesn't depend on G. The Y component, it doesn't depend on Y. So these are immediately 0. And that gives you one more result, that this component is equal to 0. So my electric field has no x component that depends on x. So if I have this, well, so my x component is, if anything, it's simply going to be a constant. All right, that's fun. So I think I can actually say this. I can say, for the part that I really care about, the time varying component, or some component that's going to change as a function of position and or time, I can say, well, this says nothing that's interesting to me. So I can say my electric field does not have a component that's waving, that's going to be position or time varying. So this is actually something that, this is a non-trivial result to right away, because this is telling us all this thing that I have been pointing out. What this is telling us is that what we are looking at is an example of transverse wave. Everyone here remembers the phrase transverse wave versus longitudinal wave? So, it's a vocabulary word. If you forgot it, go back and review it. This is what transverse and longitudinal means. This is the longitudinal wave, where the oscillation of the wave is along the direction of propagation. That's longitudinal. And transverse means the other thing, where the oscillation is perpendicular to the direction of travel. So because this is saying that any interesting variation is not in the x component, it's in the y and z component, it tells you that whatever wave you get, it's going to be transverse wave. Okay? All right, so that's interesting. So I think once question?
If it was the x component, not y and z, it would be the
yeah, if I had a non-zero x component, or x component that's not constant, if this wasn't 0, then it could be a longitudinal wave. Yeah. Yep. All right. So having narrowed down the components of electric field to simply y and z, I think I want to go one step further. I want to be able to say, well, or let me say it this way. It's going to make my next calculation simpler if I had only one of those two components. So this is what it really comes down to. So so far, I've tried to keep things general, other than I'm very, very far away from this oscillating charge, so that I can say it's a plane wave. And with that alone, I got the fact that the x component of electric field is not really changing. Now, I actually have 2 more degrees of freedom remaining if I'm keeping things general. This charge can be oscillating up and down, or it can be oscillating horizontal this way. And apparently what we are getting is that if it's oscillating this way, then we are not getting any wave along this direction. So it can be oscillating up and down, or it can be oscillating this way. I'm going to pick, without loss of generality, the one particular direction. That's going to make the rest of my calculus easier. Okay? So I'll pick up and down direction. So that would be the y direction. So what I'm going to say is that there's no interesting oscillation in the g component simply by my choice of the source oscillating in the y direction. Okay, so I will say this will be 0 by choice. So I'm only going to deal with electric field which has component in the y direction. And that'll enormously help me in going through some of the calculus now. So I guess, where should I start? Let me start from trying to get an expression that's going to be on the way to looking like a wave equation. Right? What is the biggest difference you see between the wave equation here and the Maxwell's equations here, which is also differential equation? But there's really one way in which Maxwell's equation is nothing like the wave equation here. Yes?
The order?
Yeah, order. This is second order, right? This is first order. So this taken just as it is, one will not become the wave equation. So what I have to do is I have to increase the order here. So you think of some way to do it, and I'll just tell you what to do because I've reviewed the derivation sometime last semester. So the way you can modify this equation so that it becomes more similar to the wave equation is, so the first two equations doesn't really do me any good. So I'm going to do something to the third and fourth equation. And so it comes down to I want to take a derivative. But what kind of derivative, right? And what I'm noticing is that I have a formula for the curl of each of these fields. So if I were to take the curl of both sides, then I would have to deal with the left-hand side. There's no going around that. But on the right-hand side, I would have minus. You can swap the order of derivatives, right? That's something you learn in calculus class. You can swap the order of derivatives for well-behaved functions, which is always the function we deal with in physics. So you can swap the order of the time and the position derivative. So you have time derivative of curl of magnetic field. Hey, I know what curl of magnetic field is. Here it is. So I can now just plug that in. So that's what I'm going to do here. I'm going to take this expression here, and so I take the curl. Right-hand side will give me something I want that I know how to deal with using this expression here. And left-hand side, I'll just need to work it out. Let me write it down here. So let me keep the left-hand side simple for now. It's going to be this, curl of electric field. And we'll work out later what that should look like. That's going to be equal to the right-hand side minus the time derivative of the curl of magnetic field. And this is where I look at this and plug in this for curl of magnetic field. Okay? So tell me the right-hand side. With everything that doesn't depend on time, pulled out as far front as possible. Magnetic field will depend on time, so all the time derivatives eventually apply on the magnetic field. So what you're essentially doing is you're taking this and plugging this in here. Tell me all the constant terms I get first. There's three factors that are constant. Okay, mu naught, epsilon naught, they are constant. Which is the factor that I'm implying that you're forgetting? No, so, okay, I have this, which will remain inside this. So that's not constant, so let me write that down. So the time derivative of this, so the time derivative of the electric field, which is fine. There's one term that's missing here. This expression as written is not the correct right-hand side. I mean, I won't say it's easy, but it's not super difficult either. Pedro, do you see it? Which factor is missing here? Yeah, the negative symbol is meaningful. You can't simply get rid of it. The minus sign remains. There was nothing negative here that would have canceled that out. So I need a minus sign. So you don't actually get the velocity of the wave right away. Because if you are looking at this is a negative coefficient, and you are expecting a positive coefficient. So what you are hoping is that when you go through calculus, when you do the left-hand side, you will also get a negative sign. So those two will cancel out, and in the end, give you something that will resemble the wave equation. So that's why you need to follow. It's not, if this was trivial, I would just, I don't know, I wouldn't bother doing it. It does take, I mean, you could call it tedious, but it does take a fair amount of actual math. It's not, yeah, it does take a fair amount of actual math. So let's see, the right-hand side looks pretty simple. I can just write it down one more step and say that this is the double time derivative, because that's what it is. And then I'm almost there. The right-hand side looks almost like what I want to see here. And all I need to make sure is that the left-hand side ends up looking similar to that. And that's going to take work, because I copied down curl here. Curl is it's not a simple quantity. It is a complicated quantity. So let's start writing it down and see what we get. So let me do it this way. I'm going to say, to start me off, curl of electric field is equal to, and I'll leave the outer layer alone, and I'll do the inner layer first. And as I'm doing the inner layer, what I'm going to do is any term that I recognize from the get-go as 0, I'm not going to write it down. I'll just say that it's 0 and then move on. So this is going to be the result of curl will be a result with 3 vector components. It'll have x component, and y component, and z component. Some of them might end up being 0, but it can potentially have those 3 components. So let's look at that. So these are the facts that I'll keep in mind. My E has no x, no. So for all these, I said to start out with, it only, because it's a plane wave, it's only going to have x dependence. Along the y or z direction, it's going to be constant. So having narrowed that first, from the divergence of electric field, I could say in addition that the x component was constant. So anytime I take any kind of derivative of the x component, it's just going to be 0. And my y component is only a function of x, once again by making it a plane wave. And my z component, I chose that to be 0 to make my calculation simpler. So this is something I'm going to keep in mind constantly, because that's going to simplify this work here. So here, I'm taking the derivative of the g component. OK, that's 0. I said by choice, g component is 0. And then I'm going to take the derivative of the y component, which is not 0, but with respect to z. Well, that's going to be 0, because y component only depends on x. So that's why I've made these simplifying choices, because it'll make potentially complicated vector quantity simpler. And all these are all reasonable assumptions. It's not some crazy special case that I'm bringing in. So all right, x component is taken care of. Y component. So it's x component, so that's 0 from the get-go. Z component, well, that's also 0, because we said that's 0. So all right, that's y component is 0 as well. So I have z component to worry about. Once again, all this is important. We need to go through in. OK, so the y component, derivative with respect to x. Now, that's not going to be 0. So that I need to write down. Derivative of the y component with respect to x. All right. And then derivative of the x component, OK, that's going to be 0 again. So the only surviving term is this term that I wrote down here that ends up as the z component of the resulting thing. So let me just write it down. Well, I guess I can actually leave it here. And I'm going to take another curl and let's see what we get. So when I do that, I'm going to have x component plus y component plus z component. And once again, we go through this exercise carefully, because whenever you are dealing with this gradient operator, you are dealing with the things that have components with other things that have components. That's why you have to slow down and make sure you're not mixing up components of one thing with the other. So you know, as I take this curl, this time you have to remember I'm taking curl of this vector. I'm not taking curl of my electric field vector. I'm taking curl of this vector. So some things to know about this vector: it has 0 x and y component. It has a non-zero z component. That's actually now different. And you know, this still depends only on x. So let's look at this. Then the x component, it's taking derivative g. Okay, that's not 0, but with respect to y, that's 0. All right, minus derivative of the y component, that's 0. So the x component again ends up being 0, thanks to our actually, I think x component would have been 0 no matter what. So the y component is the derivative of the x component, which is 0, the 0. And then derivative minus derivative of the g component, okay, which is not 0, with respect to x, which is again not 0. So I actually have to write that down. So it's going to be minus the x derivative of this. So that's the minus double x derivative of the y component of electric field. So you see that we are getting what we are hoping for. We are going to end up with a minus sign. That's going to cancel this other minus sign that we were worried about. Okay, let's finish this up. G component will be derivative of the y component. That's a 0. So 0. And then minus derivative of the x component, which is again 0. So the g component ends up as 0 as well. And I remember now, this is why I started making this a simplifying choice, because it made this step a lot easier. Before, when I didn't make this choice, I would have some terms written down here and here that I had to deal with, and I didn't want to deal with them anymore. So that's the result. With this simplifying, kind of a one-dimensional plane wave situation, this left-hand side ends up being minus, or y hat. So it only has y component, minus double position derivative of EY. That's going to equal to the right-hand side. So right-hand side is equal to minus mu naught epsilon naught. And then let me write out this, this electric field. We started out by assuming that this electric field only had y component, right? So let me write that down. Y component, EY, or I guess double time derivative of the EY. And this is one place where we see something that's reassuring, because the reassuring thing is that it's the same component, y hat and y hat. If these had been different components, then we would be in trouble. Like if this is somehow we ended up with, then we would have to say, well, the only way to satisfy that equation is to say the whole thing is 0. Because something that's in the y hat direction cannot equal something that's in the z hat direction. So the only way this left-hand side can equal the right-hand side if these two vectors are pointing in the same direction. And they do. They're both the same point in the y direction. And what you have is the wave equation in terms of the component. The y component on the left-hand side and the y component on the right-hand side. So minus signs cancel as we wanted. And this is the wave equation that we end up with. The one-dimensional, the plane wave equation that you end up with is the double position derivative of the y component of electric field is equal to mu naught epsilon naught times double time derivative of the y component. And so this is the kind of derivation that Maxwell went through. And this is when he realized that, well, or rather, this is his prediction of something that he would recognize as electromagnetic wave. This is a wave formed by electric field. Nothing but the electric field. It's an oscillating electric field. So what it's saying is that when I have a charge that's oscillating up and down, that causes a ripple in space. And what that ripple is made up of is just the electric field. It's not a ripple of some movement of, some physical object. It's not ripple of movement of air molecules. The only thing that's rippling in this ripple is the electric field. And, or, if we did a similar derivation, except we did it with a magnetic field, then it would be a ripple of magnetic field. And I will tell you this much without going into it too much, that it's a kind of ripple that people haven't seen before. Because when people dealt with a wave, usually there was some kind of a medium. There was something physical that you could point to, water, air, some kind of string, that this is the thing that's doing shaking. But this is the first case where the only thing that you can point to and say, this is what's shaking, is the electric field. And if you think all the way back to the humble beginning of electric field as this device here, you would think that, well, electric field, that's nothing physical. It's just a mathematical device that tells you how to calculate the electric force. And what I have to tell you is that this equation is what gives physical existence to electric field. As in, with this, we can no longer say electric field is a mathematical convenience, mathematical device. It's something that has to physically exist. And what I like to say is that anything that can kill me is not, it has to be real. It's not phantom or something that's virtual. And electromagnetic waves can kill you. What's called a gamma ray, it's an example of ionizing radiation, is electromagnetic radiation. It can kill you. So it's not oscillation of some faraway charge that kills you. It's the electromagnetic wave that hits you that's going to kill you, unless it turns you into Hulk. So this is really what gives the strongest argument to the claim that physicists will make, that electric field has a physical reality. So this is the electromagnetic wave, and I guess most of you know this final answer is what is the speed of electromagnetic wave? As in, this is the coefficient that we identify in the location of 1 over v squared. So I can solve for this 1 over v squared and say velocity of electromagnetic wave is equal to this thing reciprocal square rooted. So square root of 1 over mu naught epsilon naught. Can someone tell the class what this is expected to be? Chris? Yeah, this is supposed to be speed of light. And for Maxwell, this was actually a very significant discovery because in Maxwell's time, speed of light was actually known. People didn't know what it was. They were actually arguing over nature of light. Is it a particle? Is it a wave? Newton was the guy who had a corpuscular theory of light. He thought light was particle. And this was actually a debate that was going on in the early 19th century. Maxwell only came up with all this in the 1860-something, 1865. So by the time Maxwell did all of this, people have been arguing over what light was. Some people are saying it was particle, some people are saying it was wave. And actually the wave theorists have been winning for a while because they were predicting all these interference effects. And without understanding what kind of wave light was, they were seeing those interference effects. So people had an idea that light was some kind of wave. They didn't know what. So this, when Maxwell calculated this number, and he knew constant epsilon naught from electricity experiment, mu naught from the magnetism experiment. So plug in these two, apparently two disparate, unrelated numbers. Then he gets a number that he recognizes as speed of light, or approximately equal to 3 times 10 to the 8 meters per second. And there's nothing else that's that fast. So when he calculated the number, he recognized that as the number that was already measured from astronomy, where people were measuring the time delay in the Galilean moons from appearing, depending on the distance between Earth and Jupiter. They were noticing that those moons were appearing a few minutes later than they should have. And so based on that, people already calculated the speed of light. And Maxwell was finding this number that he calculates from this theory matches that experimentally measured the value of light. So he makes that guess that light is in fact electromagnetic wave. And it won't get confirmed for a while. There are other guys who actually did experiments to generate electromagnetic waves. And I think those might have been done after Maxwell died. And to confirm that the visible light is actually electromagnetic wave would take a longer time. But this is the biggest discovery, that something as familiar as light is actually, comes from this. It's no one would have guessed that light had a kind of electric nature to it before all of this math. So that's the derivation of electromagnetic wave equation for light. I think there's one feature that I kind of skipped over, which is probably worth not skipping over. Let's see, how do I get to that? I think the best way to get to it is through this expression here. This expression, which we kind of used without looking into too much detail of it. So let me point out the part that I want you to look at and see. So let me write down the right-hand side first, since that's something I feel more comfortable with. So let me write this down first. So the right-hand side is mu naught, epsilon naught. And I'm going to write down electric field in the form, simplified form that we have chosen. So the time derivative of y component of the electric field, which only depends on position x. Right? That's the right-hand side here. And what I want to do is I want to expand out the left-hand side so that you can say something about the relationship between magnetic field and an electric field in the electromagnetic wave. So the left-hand side, it's going to look complicated. So let me write all this out. So I think I can make one simplification so that I don't have to write down everything. So we are doing the same thing, right? So we are looking at a charge that's oscillating very far away, so that here it looks like a plane wave, which means we can say that the magnetic field as well as electric field is only going to be function of x, not function of y or z. Good? So I'm going through the same step that I did before with this. So starting from this divergence for magnetic field, what we can say is, when we say the divergence of magnetic field, or writing it out in terms of components, is the x derivative of x component, which is only going to be function of x, plus the y derivative of the y component, which is only going to be function of x, plus the g derivative of the g component, which is only going to be function of x, and all of that is equal to 0, then you see the same thing you saw last time. We end up saying that, well, this is 0 because it doesn't depend on g. This is also 0 because it doesn't depend on y, only depends on x. Since this entire thing is 0, that means this also must be equal to 0. So the magnetic field also has no oscillating x component. So my magnetic field as a vector might have a y component, which will depend on x. And it might have g component, which will depend on x. But that's it. No x component. So both electric and magnetic fields are transverse in an electromagnetic wave. And what I wanted to show here was the direction of magnetic field, given that this is the propagation direction. That's the direction that wave is moving in the sense that waves move. And this is the direction of electric field. I want to see, okay, what's going to be the direction of magnetic field? So let's write it out. Out of this Ampere's law equation, I wrote down the right-hand side. Let's write down the left-hand side with this simplifying knowledge in mind. So I'm looking at this here. I'm taking the curl of that. So let's just write it down term by term. So when I take the curl, it's going to potentially have x component, y component, and g component. Let's see which components don't go to 0. So I'm gonna simply stare at some things to argue that they are 0 without actually writing it down. So as I take the curl of this, I refer to this expression here. For the x component, I'm taking the curl of g component with respect to y. Well, that's a 0. I'm taking curl of the y component with respect to g. Well, that's also 0. So I can say x component of this is 0. Kind of good. Okay, the y component. So it has no x component, so that's a 0. G component with respect to x. All right, so that's not going to be 0. So I have to write down this is. Wait, there's minus. I feel like I'm missing something, but well, let me write it down. So I'm doing the y component, the second term. So the derivative of the g component with respect to x. So minus derivative with respect to x, bg. Feel like that minus sign doesn't belong there, but we'll see. Yeah, I think I might know why that's there. I'll have to reason that through. G component, well, let's see. It says, so y component with respect to x. That's not 0, that is it. So I have to write that down. Y component, derivative with respect to x. Derivative with respect to x of the y component of magnetic field. It's there, I have to write it down. X component, okay, that's a 0. So that's 0. So this is what I end up. And here's the reason that you might hesitate as you write down this term. Can my right-hand side have any g component? Can my right-hand side have any g component? Looking at this equation, am I allowed to have a non-zero g component? Why not? Yeah, left-hand side only has y component. But this is telling me I have a g component. So what does that mean? Well, there's really only one solution. This offending term must be 0. Right? That's the only way I can make this equation work. Or, I mean, I guess this could be a constant term. Whatever, so the oscillation term is 0. So here, with the magnetic field, I didn't start by assuming that this is going to be 0. I tried to include all the terms that might possibly appear. But because of our earlier simplification, saying that electric field is along the y direction, we had to say, well, the y component can exist. My magnetic field can only have z component, no y component. So by the way, a lot of lower division physics textbooks will give this fact to you as a as a fact that you might have to memorize. I guess you should actually memorize. But what I want to show you here is these facts that you will see cited in a lower division physics textbook. It's something you can derive from Maxwell's equations. It's something that you can theoretically figure out. And what this means is this. So, well, I'll go through the argument, and when I do it, what you'll find is that magnetic field actually points along the z direction. That's the direction of magnetic field. So, so this is always going to be arrangement of electric, magnetic field, and propagation direction. It'll always be the electric field is perpendicular to magnetic field. And both of them are perpendicular to the propagation direction. And in fact, they are arranged in such a way, when you do E cross B, then the cross product points in the direction of propagation direction. So and that's what this equation is showing. Because once you said electric field points in the y direction, then magnetic field along that direction has to be 0. So it can only have the z direction. And I guess showing that it's pointing in positive direction, even though there's this minus sign, I don't know if I want to go through that. Yeah, I should go through that detailed argument. It comes down to looking at sort of how these two are related. I guess simplest way to show is this. Let me write down a form for electric field and magnetic field as a sort of periodic traveling wave solution thing. So I might say electric field, the magnitude is amplitude times cosine of kx minus omega t. Do people remember this way of writing traveling wave? Yes, wave number times x minus omega t. This represents wave traveling to the right, or wave traveling in the plus x direction. Yes? And this is what I'm going to assert. I'm going to assert that the magnetic field, which apparently points in the z direction, also takes this form. This portion looks exactly the same, cosine of kx minus omega t. And there's some amplitude of b naught, which actually I'm trying to figure out, like how that relates to electric field. So let me plug in these two gases into this equation, and let's see what we end up with. So when I plug them in, this is what you end up with. The left-hand side will look like mu naught epsilon naught, mu naught epsilon naught. I'm going to just skip the y hat because I know I'm dealing with the y component. I'm taking the time derivative of electric field. So I'll get a factor of minus omega out, but cosine, so it'll be plus. So it'll be, the derivative will be plus omega E naught sine of kx minus omega t. Everyone okay with this as the derivative, time derivative of this function here? Okay, so I want to say that is equal to this term here minus of the position derivative here. Well, minus, and then minus sign, so minus also cancel out. And I'll get plus, and the k factor comes out, k times p naught sine of kx minus omega t. Okay. So let me see what the relationship between b naught and e naught is. So sine of kx minus omega t cancels out. It goes disappears, well, cancels out from both sides. So let me just solve it for b naught. So when I solve it for b naught, this is what I end up with. The amplitude of the magnetic field oscillation is equal to amplitude of the electric field oscillation times mu naught epsilon naught, and then omega over k. Let's rewrite these two in terms of speed of light. We know what mu naught epsilon naught was, right? 1 over v squared, or 1 over speed of light. So that's that. So this is 1 over speed of light squared. What's omega over k? Do people remember what that was? So k is related to wavelength. The wave number k is related to wavelength by 2 pi over lambda. And if you want me to write it down, omega is related to frequency by 2 pi times frequency. So what's omega over k? Can you say it louder?
Would it just be alpha over lambda? Oh, sorry, no.
Do the algebra, you can write it down. I mean, it might not be easy to just do that in your head. Lambda, so wavelength times frequency. What is that physically equal to? Wave speed. Yeah, so this omega over k, I mean, it's an expression that's good to memorize, but in case you didn't, you can work through this and get that this is equal to speed of the wave, or in this case, c. So actually, so one factor of this cancels out one factor of this, and you get this rather simple expression, which you can take as being true of any magnetic field in an electromagnetic wave. The amplitude of the magnetic field is the amplitude of electric field divided by c. It's a relationship that you find between a magnetic field and an electric field in an electromagnetic wave. It's I think actually that was one of the multiple choice questions I was asking in the one of the final exam questions, but this is a useful factor to memorize for a number of reasons. One of them being, this tells you how the units of electric field and magnetic field are related. Like, you wouldn't guess this from the beginning, but what it's telling you is that unit of magnetic field, Tesla, is unit of electric field, volt per meter, divided by meters per second. So Tesla is volt times a second per meter squared. I mean, that's a kind of relationship that you wouldn't bother memorizing. But if you know this relationship, then that's something that you can get at. And that actually makes sense with this formula here, because speed times magnetic field must have same unit as electric field. Right? All right, so that's the derivation of electromagnetic wave and some of the very basic properties of electromagnetic wave. The relationship between the direction of electric field and the propagation direction. It's a transverse wave. And the relationship between electric field and the magnetic field. So what I'm drawing here is the typical representation of electromagnetic wave with everything that we have been talking about in the last hour. So, this is my coordinate system, x, y, z, and I drew them in a perspective view this time so that I can draw magnetic fields in a way that's not out of the board and into the board. So this would be a way to illustrate what we've been talking about. So we said electric field, it's only going to have y component. And it'll be a function of x, which means at these different points along x, I can represent the different values of electric field. So if there's a point where I have the strongest electric field, then around that point, there will be a weaker electric field. You have to imagine me representing this in a snapshot form, as in I froze time. This is a moment in time. And at this moment in time, my electric fields look like this. So let me just finish drawing some of them. And so what this is, it's kind of like a vector field, except because there's so much information I need to present, I'm choosing to only draw my electric field along the x-axis. So you have to imagine this as a plane wave. There's something that looks like this, slightly offset from x-axis, either offset in the y direction or offset in the z direction. It's a plane wave. It fills the entire space that way. So I'm only representing electric field values along one line. Yeah? And what we talked about magnetic field in this situation is that it's going to point along z direction. So that's what this is, drawn in kind of a perspective view. So magnetic field, I guess this is not drawn, right? Magnetic field kind of goes this way, and this is perpendicular to the electric field. So if I just draw a few more to fill this up, then this is what this is perpendicular, and this is what magnetic field looks like. So some of the features you see here is that where the electric field is at maximum, magnetic field is actually also at maximum, and they go to zero together. And so on. All right, and once again, this is a snapshot view. So if you allow time to flow again, then you will find these two waves propagating to the right. So this is the propagation direction. And as I said, and I don't know if I can demonstrate. I'll just give this to you as a factoid that your textbook will also repeat, that the electric field cross product with the magnetic field, electric field cross product with the magnetic field, it's parallel to the propagation direction. It points in the same direction as the direction that the electromagnetic wave is going in. And you can actually prove this using the expressions that we wrote down earlier if you wanted to. And what you'll find is that if you want to say wave actually goes the other way, as in your electric field as a function of position and time, it looks like E naught cosine of kx plus omega t instead of minus omega t, then you will find that your magnetic field actually points the other way, so that E cross B points in the minus x direction. This is something that's enforced by Maxwell's equations. So let's see. What should I look at? Let me first show you this simulation. This is a simulation of radiating charge, or simulation of how electromagnetic wave is generated. So it's a PHYS simulation you can find, radiating charge. So what it simulates is simple. So when you have a charge, what does the electric field around it look like? So single stationary charge, you have a radially outgoing charge. I believe the reason it goes out like this is they are trying to illustrate the fact that the effect of electric field, it actually travels in a finite speed. If you created a charge here out of vacuum somehow, then for somebody here to notice that the charge is there, it'll take the distance divided by speed of light to find that out. So like how, sometimes astronomers say when they see a star going supernova, they say, that star actually went supernova when, I don't know, fishes were walking on land or something. Like, you've heard that, right? Yeah, so that's what they're trying to represent, that it takes time for this effect to propagate. So that's that, but once it's done, it sort of looks like a familiar picture you have seen. And I can show you some other more familiar pictures. Oh, no friction. What does that mean? I guess that means if I set it to move, then it'll just keep moving. So you can see that first time I kind of, oh wow, I can make it oscillate that way. All right, let me reset it. So let me just do these presets. When it's going in line, linear, then what you see is that these field lines don't look all that different. It looks slightly different, which if we are doing special relativity, I would look at how it's different. But we are not, so I'll just say, okay, it looks like it's radially going outward. I'm not gonna worry about that too much. And now what's interesting are, I don't know what bump does. Oh, I guess that's a bump. All right, not all that interesting. What's interesting are sinusoidal and circular. They both result in some kind of wavy thing. And I don't know if I can, let's see. Yeah, I don't think I can really zoom out. So for the plane waves that we've been talking about, this is the wave front that I want you to imagine. Let me just draw a circle that kind of looks like this. So for this oscillating charge here, this is kind of like the wave front. When you see a wave hitting the minimum here, then the minimum hits here also. So you have to imagine as you are far, far away from the charge, this curve will get gentler and gentler. And at some point, it'll kind of look more or less flat. And the reason I want you to bring up this simulation is to show you one more feature of this, how electromagnetic wave is generated that we won't really do any math in. So I have two parameters that I can control here. Do I want to go back to? Let's go back to sinusoidal. Oh, and you see that there's no wave propagating up or down, as we were saying. If a charge oscillates this way, there's no wave here. So there's two parameters I can change. I can change the amplitude. So 0 amplitude, it's not oscillating. And I can change the frequency. And this is what I want you to notice. If I make the amplitude larger, then the size of the wave gets larger, right? That seems reasonable. Like the opposite would be, I don't know, opposite would not make any sense. Like it will be like homeopathy. So all right, so smaller amplitude means a smaller amplitude of oscillation means a smaller effect of wave here. Now here's one more thing that's interesting to see. Watch me increase the frequency. And when I increase the frequency, frequency of oscillation gets larger, but one other thing gets larger. Let me go back to lower frequency so that you can see. Oops, that's 0 frequency, lower frequency. It's probably easier if I draw it. Let me do the larger frequency, and let me draw this line of waves. I don't know why it's getting larger as it gets farther away. I think that's unusual. But let me make the frequency smaller. So what this is simulating is that the amplitude of the electromagnetic wave that's produced, it depends on frequency. If this is oscillating more frequently, it'll actually produce a larger amplitude of wave. This whole thing is covered in something, or if you want one keyword that would lead into all of this, it's called a dipole radiation. And it is upper division level topic that we won't really talk about any more than this. So this simulation illustrates those features of electromagnetic wave. And before I go into applications of electromagnetic wave, let me just show you one formula that's actually pretty useful and important. And that one formula will be, useful in the sense of, I don't know in what sense. You're not going to see this on the test. But think it's useful for you to know that one formula that you should know is something called a Poynting vector. And I want you to note Poynting is spelled weird. It sounds like a pointing as if I'm pointing, and it's confusing because the Poynting vector, it points in the direction of propagation direction, but it's spelled with a Y. I think it's named after a guy named Poynting. Anyways, the Poynting vector, let me just bring it up here. Here, maybe that'll get me to the formula page. I haven't really looked where Poynting vector is here. Wait, there it is. So this is the formula for Poynting vector. Can I get rid of? I wonder if I can just open this in. Sorry, I haven't used this textbook in this particular format or before. Okay, let me just leave it here. This is the thing called the Poynting vector. So this thing called Poynting vector. The key important part is the E cross B. That's the part that tells you what direction it's pointing in and what direction the propagation direction is. And the coefficient in front is important too. Once you have the correct coefficient, 1 over mu naught here, then this Poynting vector actually says something specific. It says this. It says, so I guess there's a couple different meanings you can assign to this. I'll just say 2 meanings you can assign to it. So I hope I have them memorized correctly. The first meaning you can assign to it is the rate of momentum transfer. I want to say per area. Well, per area. And the thing that I was hesitating on was if I should say this also per time or something. I better figure out the units here. So let me first figure out the units here because that's going to help me. So this is what I can do. I can actually, so this can be rewritten in several different ways. Let me rewrite it in one way that's kind of useful to me. So in both of these rewriting exercises, this is the relationship I'm going to exploit. I figured out the relationship between electric field magnitude and magnetic field magnitude before, right? So the magnetic field magnitude was electric field magnitude over C, or the other way around. Electric field magnitude is C times magnetic field. All right. The other information that's going to be useful for me to remember is speed of light c, or rather c squared, is equal to 1 over mu naught epsilon naught. So using that, I can rewrite this in a couple different ways. The first way is going to be actually pretty meaningful. So let me rewrite the electric field amplitude in terms of magnetic field. So in that case, I get this expression. So it's going to be pointing in some direction. Let me call it lowercase s hat. So some direction, and I'm writing down the magnitude of the vector. It's these two are perpendicular to each other, so there's no sine or cosine to worry about. So CB times B. So this is C times B squared over mu naught. Does this quantity remind you of anything? B squared over mu naught? What do you guys remember about the electric energy density in electric field and energy density in magnetic field? Right? That's another useful formula to memorize. Energy density in electric field is 1/2 epsilon naught electric field squared. energy density in magnetic field is 1/2 mu naught magnetic field squared. So so from that alone, what that tells you is that this particular combination must have units of joules per cubic meter energy density. And it turns out that this is actually the energy that is stored in this particular region due to this electric and magnetic field being there. Half of that is in the magnetic field, and you can actually rewrite that to get the other half that's in the electric field. So that's what this expression is: energy density times speed of light. So there's a speed of light is in the unit of meters per second, right? So one way I can rewrite these 3 units, or these units, is meter cancels that out, so it's a joule per second times 1/meter squared, right? What's a joules per second? Energy per time? What physical quantity does the energy per time represent? It's in unit of watt, representing power. So this is power or watt per square meter. Or this is, power per area. And this is a quantity that has a name. In the case of a radiative power, this is what we call intensity. So when you look at something like a laser beam, it has a high intensity, mainly because it's a certain amount of energy focused down to such a small spot. So, high intensity, high power per area. But in terms of the total amount of power output, this projector has much higher power than this laser pointer does. But when you look at any single point, the laser is brighter because it has higher intensity. Good. Okay, so that's what the unit here is telling us. So Poynting vector, as it is, it actually represents intensity. So you can just take the Poynting vector as it is, and that's actually the second meaning of Poynting vector. What Poynting vector represents, the magnitude of it, it tells you the intensity or power per area of electromagnetic wave, which is often but not always light, visible light. Right? All right, I still need to figure this out. So what I wanted to say was the rate of momentum transfer per area. Let me work out the units and see if I need to divide by anything. I don't know why I thought I wouldn't need to, but let's, so rate of momentum transfer would be the rate of change of momentum, dp dt, per area. So working out that unit, momentum is kilogram times meter per second squared per second times 1/meter squared. I want to rewrite this in terms of joule, so I'm going to multiply top and bottom by meter. Instead of canceling anything, I will say meter squared, meter third. Then this is joule. So this whole thing is watt. Watt per cubic meter. Oh, I see what it, wait. Per volume? Yeah, so rate of momentum transfer per area doesn't have correct units. So I don't want to say rate of momentum transfer per volume either. So if I want to have correct units, then this would have to be length. Don't know if that makes any sense. Rate of momentum transfer per length. I don't know. This is related to something called momentum flux, and I think I'm pretty mixed up there myself. I'm not sure if I remember. So the biggest meaning that you assign to Poynting vector is the intensity. That's the biggest meaning. That one I know is correct. I wanted to say something about momentum because this is related to how much force is exerted on a charge exerted on a matter by light. So you might have, I'll just show you this as an example of application of electromagnetic wave. This is a pretty unusual application, but it's an interesting application. So if you Google solar cell, then you will see what that's about. So it's a cell that operates by, there was a good picture of it somewhere. Let me Google search Icarus. So people have been talking about solar cell for a long time before something real actually got launched. This is something real that got launched not that long ago. So this is a solar cell spacecraft. Its main propulsion mechanism is that these are reflective, very light material that's reflecting sunlight. And so I'm trying to tell you guys that this electromagnetic wave is real, that it has a real physical meaning, physical quantity. And there are two senses in which this electromagnetic wave is real. One, it carries energy. That's what's represented here. And two, it carries momentum in whatever combination that's actually correct. But key thing is that it actually carries momentum. So as this light is either absorbed or is reflected back, there is a change of momentum. So this must be absorbing that momentum. So there's a force on this to move forward. So that's the idea that solar cell is based on. And this got launched in like 2012 or something. And it actually works. It's a proof of concept that solar cell, whether it's practical or not for actual space travel, that it actually works. That by reflecting sunlight, you can propel a spacecraft. Now, that's not the most common application of electromagnetic wave. Aside from light and lasers, the most common application of electromagnetic wave is radio waves. That's sort of ubiquitous. You see it everywhere. I guess especially if I include microwaves by radio wave, because your cell phone works on microwave frequency. Later. So this is a simulation that kind of illustrates what that radio wave looks like, or the generation of radio wave. So you imagine this as the radio station, and this as your receiver. This is how radios kind of schematically works. Something in the transmitter wiggles the electron in the transmitter, and this wiggling, it produces this wave of electric field that wiggles the electrons in your receiving thing. And I guess this shows curved vectors. Let me show you the full field. That's the fun one. So that's what the full field electromagnetic electric field looks like. So it's only showing the time varying component, because if I have charge here, there'll be, but antenna is electrically neutral. So that's why this single charge just moves up and down, there will be change in the electric field. And that's what this is showing. It's showing those changes both in terms of the one component that's pointing away from this charge, that's the static field, and what's called the radiated field. And it's only showing the radiated field. So this is the static field. So as I move it up and down, you see the static field changing, right? And that static field, its magnitude doesn't really change regardless of how fast this moves. And it goes down pretty quickly. But the radiated field, when you look at the radiated field, that its magnitude depends on how quickly I'm shaking it. And it doesn't really die down all that quickly. It travels a very far distance. So I thought I could actually put this on oscillate. Okay, I want to put it on relatively small amplitude, relatively larger frequency. So this is what electromagnetic wave radiated field from this looks like. So if you track a particular arrow of a particular height, you see it traveling across, right? And if, on the other hand, if you're looking at a single point, the electric field is oscillating up and down. And this oscillating up and down field is what's shaking this. And this operates on the carrier frequency of 98.7 megahertz. And when you tune your receiver circuit so that it's in resonance with this carrier frequency, then you would receive the signal. And the way signal is encoded, it's a whole another matter, frequency modulated versus amplitude modulated. Everyone here knows about electromagnetic spectrum? Yes? Yeah, okay. I'm kind of out of time anyway. So, this falls in the kind of on the lower end of the spectrum. As you go higher, you get microwave, infrared, visible, ultraviolet, X-rays, and then gamma rays. All those are electromagnetic waves. The only difference being the frequency. Is it slower frequency or is it higher frequency? So, that's the subject of physics 4C. We spend a lot more time dealing with electromagnetic waves and optics. But for the purpose of this class, I think this is where we wrap up. This is all the topics we have time for. And on Wednesday, we will spend the time on exam review.